Welcome to the deep dive. Have you ever had, a really specific question about your company's data? Like, how many first class tickets did we actually sell on Tuesday's last quarter? But maybe you don't speak SQL. You don't know your select from your joinware. Well, this deep dive is definitely for you. We're looking into text to SQL today, sometimes called NL2 SQL. The big idea here is to build a bridge, a really solid one, between plain English questions and these huge complex databases. Think Google BigQuery, the ultimate goal, making data accessible to basically everyone, no coding required. So our mission today is to dig into the sources, explain the architectures, the prompting techniques that models like PaLM2 need to use to make this text to SQL thing not just accurate, but also scalable, especially for really complex cases. Let's keep a picture in mind. Managing a massive flight reservation system, that feels like one of the most complex data sets you could imagine.
Yeah, that flight reservation example is spot on. It really gets to the heart of why this is so difficult. Generating SQL accurately, it's complex. It's not just one command usually. Think about asking something like the percentage of international flights that were late. The system has to chain commands. It needs to link, say, the customer's table, reservations, flights, maybe even delay codes. It gets complicated fast. And data engineers, they spend ages, sometimes days or weeks, writing these queries, tuning every join. If an LLM is going to step in, it needs to handle all these relationships across multiple tables, multiple steps, and do it basically instantly.
That's a massive challenge. Okay, let's unpack this. How do we even start equipping an LLM to deal with that kind of complexity? The first really big problem engineers hit is just schema overload. Think about that flight system again. Maybe you're on BigQuery, you've got hundreds, maybe thousands of tables, or even just a few really wide tables with thousands of columns. If you just dump all that schema info into the prompt, well, the LLM gets overwhelmed.
Exactly. It's like handing someone the entire Library of Congress catalog and saying, find this one specific fact. It's just too much.
So architecture is key then.
Right. The simplest way, let's call it pattern one. Intent detection and entity recognition works okay for smaller data sets. Where things are more contained, how it works is pretty straightforward. The system figures out the user's intent, identifies key things, entities like ticket type, last week. Then it grabs the schema info for the tables it thinks are relevant, bundles it up in a prompt, and asks the LLM to write the SQL.
Okay, so that's good for replacing maybe older systems.
Yeah, it's often simpler to design than, say, rule-based systems.
Yeah.
But it hits a wall pretty quickly. If you add something new, a new kind of loyalty program, a new fee, you often have to manually update it, maybe add new examples to teach the model. It's not very flexible for things it hasn't seen before.
Right, which leads us directly to pattern two, LLM flow with Retrieval-Augmented Generation, RAG. This seems like the approach designed for that enterprise scale for flexibility, so instead of the whole library catalog.
Exactly. RAG uses semantic search, embedding strategies. Think vector indices.
Like a really smart librarian.
Kind of. The system looks at the user's question, understands the meaning, the semantics, and retrieves only the relevant bits, the right datasets, tables, columns, before it even tries to generate the SQL.
So it prunes out all the irrelevant stuff.
That pruning is absolutely crucial. If someone's asking about their seat assignment, the LLM shouldn't need to know about catering or fuel prices. RAG focuses the model's attention. That's what makes it scalable for those huge datasets, those wide tables you find in BigQuery or Snowflake.
Okay, but Aragus sounds like it adds a whole new layer of complexity itself. Managing those vector indices, making sure they pull the right data, that's another system to maintain, right?
Oh, absolutely. It adds pipeline complexity. And your embedding strategy has to be really good. The trade-off often involves sometimes pulling in slightly irrelevant information. If the embeddings aren't perfect, maybe you get a few extra columns, and that creates a bit of that schema interference we were talking about, which then needs fixing later down the line.
So getting the architecture right is step one. But then the accuracy seems to depend not just on which schema parts you show the LLM, but also how much context you give it.
Precisely. And this is where good RAG systems really shine. They need to pull metadata, sure, schema definitions, data types, foreign keys. But the real game changer often turns out to be sample data.
Sample data. Okay, this crops up a lot in the research. Why is seeing a few rows of data so much better than just having the column name and type?
Because schema alone can be super abstract. Like you see a column, status code int. What does that mean?
Could be anything.
Right. But then you show the LLM a few sample rows. You get a row 1, 2, 99. Instantly it gets it. Okay, this isn't just any number. It's probably category code. So the recommendation now is usually to provide, say, 3 to 5 representative sample rows for each relevant table. It makes a huge difference in comprehension without making the prompt enormous.
That makes sense. But I read something even more surprising, that LLMs can sometimes infer relationships between tables, even if there is no explicit foreign key defined. So if customer shows up in two tables that aren't formally linked, the LLM might just figure out the join. Isn't that kind of risky? What if the data's messy or names are reused?
That's a fantastic point, and it highlights the risk-reward here. Yes, research shows they can be quite good at spotting potential joins based on column names or patterns in the sample data, even without formal foreign keys. Which is powerful because, let's be honest, real-world databases are often messy. They're not perfectly structured. But it is risky. The model is making an assumption. If it assumes, say, date created in one table is the same thing as date shipped in another and tries to join on them, you get garbage results.
Logically wrong, even if the SQL runs.
Exactly. And that's why these reasoning approaches we're about to get into are so important. They help catch those kinds of errors.
Okay, so here's where it gets really interesting. We're moving beyond just smart prompts to using techniques that specifically help the LLM reason, especially for those harder multi-step questions.
Yeah, we're talking about decomposition and multi-agent frameworks. You see systems like MAC-SQL, DEA-SQL becoming more common. They basically try to mimic how a human analyst thinks. A complex problem like, find the average flight delay per airport, then show me only the airports worse than that average.
That's multiple steps.
Right, so the framework breaks it down, uses a sort of chain of thought approach. First, figure out the average delay, then write the SQL to filter based on that result. It creates intermediate SQL steps. And within these frameworks, there's often a really key component, the selector agent.
Okay, what does that do?
Think of it as the gatekeeper for schema. Its main job is to look at the sub-question the system is working on and make sure only the truly necessary tables and columns get passed to the next stage of SQL generation.
So it actively minimizes that schema interference problem we talked about.
Exactly. By getting that initial schema linking step right for each sub-problem, performance goes way up, especially on those hard and extra hard benchmark questions.
But even with decomposition, things can still go wrong. The LLM might generate SQL that looks okay, maybe even runs, but is just flawed, especially if the user's question was a bit ambiguous. So the LLM needs to check its own homework, right? Self-correction.
That leads us to pattern 4, autonomous self-correction. Here, the system doesn't just generate SQL, it tries to run it. If it gets an error back from the database, table not found, syntax error, whatever, it feeds that error message back into the prompt.
Telling the model, hey, that didn't work, try again, here's why.
Exactly. It's powerful for fixing those runtime errors.
But what if the query runs fine but gives the wrong answer? The database won't complain.
That's the limitation. Execution feedback alone isn't enough for logical errors. That's why leading frameworks now use guided correction. Take SQL-of-Thought, for example. It uses a very detailed error taxonomy. We're talking 9 main categories of errors, broken down into like 31 specific subtypes.
Wow. Okay, so it's very specific feedback.
Super specific. Instead of just error, the feedback might be, you used a left join here, but the logic required a full outer join. Or, you included this extra column that wasn't asked for and messes up the grouping.
That sounds much more helpful than just failed to run.
It's critical for fixing those subtle logical flaws that pure execution checks miss entirely. It guides the LLM much more effectively.
Okay, so pattern 4 fixes errors. What about making good queries better, faster?
Yep, that's pattern V, self-optimization. So the system gets a query, it runs, it gets the right answer. Great. But then it might try generating a few different versions of SQL that also get the right answer.
And compares them.
Exactly. It executes them and checks, say, the execution time or the estimated cost. Then it picks the fastest or cheapest one. You might see it add a limit clause to a subquery to make it faster, or even use database-specific instructions, like optimizer hints. Things like use an NL to suggest a nested loop join.
So it's actually telling the database engine how to run the query more efficiently.
Precisely. It's aiming for production-ready speed. The catch, of course, is cost.
Because you're running the query multiple times just to test.
Right. It costs more in compute cycles during the generation phase to find that optimal query.
Okay, with all these complex patterns, agents, correction loops, how do we even measure if one approach is better than another? What are the standard benchmarks?
Good question. The main metrics you'll see are execution accuracy, usually called EX, and exact match accuracy, or EM.
What's the difference?
EM is super strict. The generated SQL has to match the reference, the gold standard query, almost character for character.
That sounds tough.
It is. and often not very practical. That's why EX, execution accuracy, is generally preferred. EX just checks. Did the generated query produce the correct result when run against the database? It doesn't care as much about the exact syntax.
Because there might be multiple ways to write a SQL query that gets the same answer.
Exactly. If I ask for the oldest customer, and the LLM writes a slightly different but valid query that still gives me the right person, EX counts that as a success. EM might fail it.
Okay, EX makes more sense for real-world use. Now, despite all this progress, we need a reality check. There seems to be a pretty big gap between how well these systems do on benchmarks and how ready they are for complex real-world enterprise scenarios.
That's definitely true.
We have the classic Spider dataset. It's huge, 200 databases, over 10,000 questions. Great for testing if a model can generalize to databases it hasn't seen. But then there's Spider 2.0, and this seems like a different beast altogether.
It really is. Spider 2.0 is designed to model actual enterprise workflows. We're talking complex cloud databases like BigQuery or Snowflake, sometimes with over 1,000 columns. And crucially, it often requires generating multiple SQL queries that depend on each other, reasoning across different parts of a project codebase, not just firing off one isolated query.
And the results on Spider 2.0 are sobering.
Very sobering. Right now, even the best models, state-of-the-art like GPT-4, are only solving about 6.0% of the questions correctly on Spider 2.0.
6%? Wow, that is low. What makes Spider 2.0 so much harder? Why that massive drop?
It's really that multi-step workflow aspect. In a real business scenario, you don't just ask one thing. You might need to, say, check available flights, then check reservations for seats on those flights, then check the price, right? Each step depends on the last one.
And Spider 2.0 tests that whole chain.
Exactly, across these really large, complex cloud database environments. That 6% number, it really hammers home the gap that still exists before these systems are truly enterprise-ready for complex tasks. These multi-agent systems are trying to bridge that gap.
And the problems go beyond just getting the right answer eventually. There's robustness too, right? How easily do they break?
Absolutely. Robustness is a huge concern. Research using benchmarks like Dr. Spider shows that models can be surprisingly brittle. If a user uses a slightly different word, a synonym the model hasn't seen, or maybe abbreviates a column name.
The query just fails.
Often, yes. Or if someone in IT just renames a database column from, say, customer to custrif, a totally normal thing to happen, the whole text-to-SQL system might just break down. That's not acceptable in production.
No, definitely not. And what about speed? Efficiency?
That's the third big pillar. It's not enough for the query to be correct. It needs to be reasonably fast and not cost a fortune to run. There's a metric for this, too. The Valid Efficiency Score, or VES. It basically compares the runtime of the correctly generated SQL against the runtime of the known good reference query.
So holding the systems accountable for performance, not just accuracy.
Precisely.
And then there's the elephant in the room for any enterprise tool, especially with sensitive data like flight manifests or customer info, security and governance.
Critical. Absolutely critical.
If we're making it easy for anyone to ask questions in plain English, we need incredibly strong guardrails. The SQL that gets generated has to respect all the existing rules, row-level security, who's allowed to see what data.
You can't have a situation where someone asks an innocent question like, show me recent bookings, and the LLM accidentally generates SQL that bypasses security and returns, I don't know, VIT passenger details or credit card info.
Yeah, that would be catastrophic.
Yeah.
Embedding those complex governance rules into the generation process sounds incredibly hard.
It is. It's a major ongoing challenge. So if we connect this to the bigger picture, you see the whole focus shifting, right? It's not just, can the LLM write some SQL anymore? The real question now is, can the LLM write the right fast and secure SQL query for a massive, unfamiliar enterprise database, often as part of a complex multi-step process? That's the goalpost now.
Okay, so to wrap up this deep dive for you listening, the main thing to take away is that text-to-SQL isn't simple anymore. It's evolved into this complex multi-stage process. The most promising approaches are mixing and matching different tools. RG to select the right data first, then specialized agents for reasoning and breaking down problems, and finally these smart correction and optimization loops to refine the output. It's becoming very modular, very multi-agent.
That modularity seems key.
Definitely. And we'll leave you with this final thought to chew on. We heard that just adding a few rows of sample data dramatically boosts accuracy. It makes you wonder, What other crucial context, what non-obvious bit of metadata are we still missing? Maybe something about a column's real business purpose, or how its values are typically distributed, or its hidden connection to some business rule. What key piece of knowledge are we failing to give these LLMs that could unlock that next level of performance and really close that gap we see on benchmarks like Spider 2.0? Something for you to think about.